Hey everybody, welcome again to the second Nexus. We can tell that December is a full month because it seems that less people than last one, but for sure we're going to keep on doing it every month. And hopefully we're going to build an interesting conversation after this. We have more time this time because we ran out of time last one, so hopefully this discussion is going to be happening in a much larger extent. And next time it's going to be in January, so that's how we're going to continue doing this event. So I want to first welcome some of the guests that we have here. We have Jill Fredson, who was a student in the AA recently. He's been doing amazing work, and he was featured in the 3D print show. Tom Smith, with a really beautiful work from diploma number 23 in the Bartlett. Vlad Tenu, close friend, his work in minimal complexity has been exhibited all over the world, almost, and he's still working on it, I believe. And Ryan Mehana, which was one of the featured speakers as well, had to cancel, so we actually did a small swap. His friend George Provenza from AAC as well is going to show us his work, so I'm very excited to see what he's been working on as well. We have a special guest, Arthur Manning, in a way trying to kind of extend the arms of the Nexus as an instance of really kind of collaboration between different universities. It's not all about the Bartlett, maybe the Bartlett part we could just get rid of and call it the Nexus. In the sense that it's really trying to, people that from architecture, designers, and different disciplines can actually come here, show their work, show what they're struggling with, and perhaps they're going to find a place where they can meet someone that could just help them take the next step forward. Hopefully collaborations will start emerging from this atmosphere. We have a bar as well, so feel free to, at any point, just get a few beers and sit closer because the conversation now we're less, we could just make it a bit more intimate. My name is Jose Sanchez. I've been running a unit here in the GAD department, and I'm organizing this event, and hopefully if you have any suggestions, just let me know. The feedback is welcome, and we're going to try to keep doing it better and better. So with that, I'm going to just leave you with Jill.
Good evening. I have a call today. So I'm going to carry through the lights. So I'm just going to show a little bit more, just a selection of projects, and through showing that, try to explain the idea of object-oriented design, which is something that is going around in a lot of universities recently, since 1 or 2 years, that also Jose, for example, is very interested in. And also, it's kind of linked to the whole idea of creating a community of people that will do something, kind of see what happens from there. So the idea, one of the ideas is of object-oriented design is actually that you shift away, it's a philosophical movement where you shift away the kind of human-based perspective to a perspective where humans are equal to other objects. So that there's no distinction anymore between the human world and the world of objects. And in the same way, it's also the idea of ecology of nature comes from, because you're actually saying that as humans are on the same scale philosophically as other objects, there is no more nature, and everything is an object. So we've been using for the moment a kind of very neutral and basic definition of OOD, which is partly collaged from Wikipedia and some other sources. So it's basically, the interesting thing about OOD is that it's both a philosophy, it's both a way of computer programming, it's a way of how people start writing books, so it's a general kind of cultural movement. And basically you could define it as the process of planning a system of interacting objects for the purpose of solving a problem. So instead of just in a linear way trying to solve a problem, you actually set up a system, kind of ecology with different objects that through their interaction it actually solves the problem. And that's also the way how many people in processing work, where you actually define computational concepts or objects that you will afterwards launch in a kind of world, in a kind of ecology where they will create a final object. And the idea, a little bit of ecology without nature, and idea of this object-oriented ecology is that we actually go away from a kind of romanticizing of nature, so that we will see, for example, a system of swarm intelligence with these beautiful birds flying around. They also start seeing this as a kind of broader political or cultural phenomenon, and kind of strip it down from a romantic vision of nature. And one thing we're also personally interested in and kind of trying to work through is trying to get rid of this kind of indexicality in computation. Like, it seems a lot of computational projects are taking kind of typical natural systems and projecting those onto architecture instead of actually computing architecture. So they're actually computing an image of nature onto architecture. I mean, everyone knows probably the kind of catalog of computational systems that have been appropriated to use in architecture. And in the end, it's a very strange act, I think, because in the end, you can always say, oh, this is a Turing pattern project, this is a fractal project, this is a flow line project, you know. And so it's kind of like a shopping mall mentality where you shop for your interesting system and then you apply it to a project. So we're kind of trying to see this as more a simulation of an architecture project than actually being an architecture project. So we're trying everything I do is kind of trying to focus on the actual tectonics of a project, and not on the kind of, you know, not on the projection of a natural system on a project, which in a way is very interesting. An interesting precedent of that kind of project is, in a way, arts and crafts, which had a very political agenda, but purely through design. So yeah, that's background. So one thing we've been working with a lot is a combination of agency and matter through the idea of springs. Like there's a lot of things you can calculate through springs in terms of defining material properties. And actually, a way how these advanced computer simulations for physics in the movie industry, for example, are working is always through a certain definition of spring behavior. So you can define any kind of material purely through how particles are related with springs. And then what we are doing as designers is that we, through agency, we're not using agency as a kind of indexical system that is trying to mimic anything from nature, but we're actually using the basic algorithm as a method how to embed design intent at a very low level in our material distribution. So if you have a lot of material and you want it to take a certain shape, instead of exercising kind of top-down control, we're actually trying that through bottom-up control. And my student project at the DRL is a good example of this approach. So this was a project together with 3 teammates, all work at DRL as collective. So I also present it in a way as a collective project, although my teammates are not here. Because I think it's an interesting example. If Jose is talking about like setting up collaborations, I think it's good to say that a lot of this work is, actually all the work I'm showing is done in collaboration. So in DRL, there's an interesting kind of Bartlett style trend taking over the DRL, in which projects become very much narratives. So instead of actually working more, like DRL has in a way a tradition of very much working through design itself, and less through narrative, but I have the impression at least that recently more and more projects are actually shifting the focus more to narratives. So we were doing the most banal project you can probably imagine, just a house, a single family house, which was then again incredibly radical within the DRL because it was small scale and it was just a house. And we were basically working with 3D printing and trying to reimagine 3D printing for architecture. And there are 2 precedents. There's Enrico Dili, who has a kind of stone printer, and there's Kosnevich, who's a professor somewhere in LA, who's clearly an engineer, the way how he sees 3D printing. And both of these guys actually cope with the same problem, the inherent paradox of 3D printing in architecture, that you have to first build a printer that is bigger than your house in order to print your house. So we were interested, both of these people are also printing in compression-based systems, which are very heavy, very slow. So we were interested into shifting that compression-based, almost Roman building system into a much more modernist idea of construction, which means that you construct off-site, you construct lightweight, and you construct everything in tension. Because we don't, the fact is, if you go into this really Roman compression-based system, like Enrico Dini and Koshnevis is doing, you actually have more formal constraints than when you wouldn't 3D print it. Because everything is compression-based, you actually have to start making buttresses, you cannot do certain overhangs. So it's an incredibly constraining system, which is kind of the second paradox of 3D printing, that in the end you constrain yourself more than if you wouldn't 3D print. So we opted for the kind of tradition of Heinz Isler, Frei Otto, to look at more material behavior, but therefore print off-site. And currently off-site there are incredible printers available that already print 600 dpi, that are 4 meters big. So there's a real market there. And we wrote, I'll explain this through a little video. Where's my notes? So we wrote an algorithm that was basically consisting of a massive mound of springs. It's kind of a massive cloud of springs, and for every point in this cloud, we're evaluating forces. So basically, we put a force on this cloud. You really have to imagine this is basically the same thing as Frei Otto's hanging chain experiment, but it's a 3-dimensional cloud of hanging chains. So for every point after it's put under pressure, we can register a specific force of deflection. We know whether it's in compression or in tension. We know its behavior. We know where it's shifting. So for the moment, this guy is sagging. And then we trace main directions of stress through the system, which become the stress lines in 2 directions, in tension and in compression. And then we assign kind of nodes on these stress lines, and every node inherits the information of our initial voxel grid. And then it starts building a kind of proto-geometry that uses the information of stress and deflection to build connections to its neighbors and construct a stiffer structure. So these are literally thousands of agents, if you want to call them like that, that are building proto-geometry and slowly kind of reinforcing. So in the end, you get a structure in which matter is purely organized on lines of stress, and is producing both the space and a kind of ornamental quality to the project. So you get this very fibrous structure. And then there's some bundling also here. So that's basically. Yeah, so that's a process in short. And this is basically how the building gets constructed. So this is the whole set of compression lines, tension lines, and that's how it runs through. This is the basic information of the stress, and that's after the algorithm starts creating the material distribution. And you get an incredibly high-res structure, which is partially between structure and ornament. And we went through a whole process, an iterative process of creating space. So initially this thing literally just starts up as a massive block of matter, similar to this one, just a cube. And then we start slowly eating away material until we kind of carve out space. We deliberately went for a very modernist open floor plan condition in the front, with a big cantilever roof. And then that kind of created a lot of more pocket-like, poche-like spaces in the back, which we found interesting because you get kind of two archetypical spatial conditions. That's the house cantilevering over LA. These are the two daughters of the house. That's the family. We deliberately put in all kind of 50s furniture as a kind of pun to the classic case study houses. And then as we were working with 3D printing, all of this geometry is 3D printable. But it's so high resolution, this is literally gigabytes and gigabytes of information. And we could never display it. You could only see it piece by piece in our algorithm when we were running it. But in the end, you could never even open this in a 3D program because there's too much information. Every line you see here has a triangular section. It was not possible to do it with a square section because that would already increase the data. It would make it too big. And the interesting thing is then we were actually, we wanted to print exactly this. So every little line would become a 0.7 millimeter thin fiber, and it would be structural, purely load-bearing on this 0.7 millimeter thin fibers. And to do that, for two reasons, we actually had to cut our building in pieces. First of all, because we're printing it off-site, so it has to be transported to the site. So we developed a whole kind of tectonic logic through working through 3D printed puzzles of how we could assemble these pieces without glue, but just purely through interlocking pieces. And then finally, finally we got from Materialize, which is a very big 3D printing company that decided to sponsor our project. They sent us 32 fibrous pieces that they had a hell of a job printing this. Because basically that's the second reason they could hardly print one of these pieces with their current printers. Not in terms of, like purely in terms of making G-code for every piece. Because it's so detailed that the amount of data that they have to feed in the printer was already on the edge. So you could never, for the moment it's impossible to print the whole building in one go, just because it has too much data. These are some of the pieces we got. So they're all you see these stress lines, so sometimes they're very straight, which means they actually have a lot of force running through them. Sometimes they're much more fuzzy, which is when the algorithm can much more kind of do what it wants to. There's some of these pieces. That's the actual thing assembled thing. So it's cantilevering out of, you can't really see it, it's cantilevering out of a surface, purely load-bearing on these thin fibers. That's some material shots there. These are the fibers. And you see they have different qualities because the algorithm, when there's not a lot of stress, it actually kind of produces some more random ornaments. And when there's a lot of stress, it will produce more straightforward structures like these ones. So these ones are clearly under a lot of stress, those not. Then we also imagined in a way some kind of, what we would do if we would have objects to print as transparent pieces for print, but Object didn't want to sponsor us, unfortunately. There's the thing in front. Then there's a lot of the internet, and also for ourselves, we always call it the dinosaur. For some reason, it really looks like a dinosaur, which is not so amazing because in a way, the way how the algorithm works is really similar to bone grout, because it only arranges material where there is stress, which is the basic rule behind how bones are organized. And bones also appear in all different pieces that kind of fit together in a very intrinsic way. So in a way, it's kind of normal, it's kind of logical that these two things look like each other. And then I'm going to quickly show some things, some workshops actually that I've been running together with Isaïe Bloch, a friend of mine from Belgium, who's working with Iris van Herten recently. So the idea here is that we use an object-oriented method of dealing with what we call radical heterogeneity. So the idea is that we find this kind of postmodern Rem Koolhaas-like collage very fascinating in the way how we can organize complete diversity and complete radicality. And we were interested to know if you could create something that we call a non-representational collage, which would mean that you would set up basically a script that contains a lot of objects that are completely alien to each other, concepts that have nothing to do with each other, and that actually interact and together would create a kind of a collage, but through interaction. So you would actually redo this postmodernist project through object-oriented programming. And then that process of interaction would be, you could also call that formation. So it's actually, the tagline then was formation as a strategy to deal with unfiltered heterogeneity. So we're trying to test this in a series of workshops. Like this is, for example, some of the things we're interested in is kind of more, is it possible to have concepts that are more meaning-based or even archetypical or very predefined that then kind of collide with matter? That is kind of, because that was one of the things we found frustrating in this project, that in a way you have so much data, you have so much matter, and so the only meaning it has is in a way structure or kind of a very harsh algorithm. So we were interested in, if you have so much data, why not try to kind of imprint kind of idea of meaning or matter in there? So we were deliberately, this is a dog, for example. So we're kind of deliberately working with, trying to embed meaning or within these computation systems. This is one project that came out of our workshop in Ghent, in which a group of Germans set up a system in which two completely different objects, one very kind of tensile, weird alien object was structurally tearing apart a more predefined, typical architectural structure made of trusses. We spent an amazing amount of time after these things calculated in processing the interaction between these two objects, which are completely foreign to each other, but one of the objects manages to, in a way, destroy the other object. And they spend an amazing amount of time really detailing out these bridges and trusses, the deformation of that archetypical architectural system, and then with that kind of alien object hanging in between that caused the destruction of the first object. So in a way, that's something we start to find interesting because we start to calculate things, kind of more banal architectural objects, and it's not necessarily high-tech anymore. So this would mean we could even calculate buildings like this in a way that you could try to figure out the interaction between a more banal architectural system and a high-resolution system. Another project where we tried to work more with that idea of predefined meaning was a group 3D scanning an ornament that was found on site. They were both doing this digital and analog, so they were also making kind of imprints with latex of the structure. Then we were using the 3D scan as a stamp in ZBrush, kind of to distribute the ornament on the surface. And then the flow lines that are predefined in the ornament would become a driver for an agent-based system, where we also tried to put in high resolution with literally hundreds of thousands of agents that are navigating the surface and distributing kind of small analog system. Then this was some of the outcomes. Then that's obviously, I mean, this is work from 6 days, so it's really fast. It's not so refined. These are some things we did at the same time as well. That's actually the same physical model of this guy, where we also start following tracing flow lines with these wires, and then we have a completely different computational object navigating the top, which is just kind of shingle-based structure. That's also something we really like, that kind of matter-based physical models. That's another one. So this was a bigger version of this previous model, where then also wires and these little seats here are in a way following the initial flow lines set out by the equipment. Yeah, so that was the presentation for now. Thanks. Who's next? You want to switch? Oh, yeah.
Hi, my name's Tom. I recently graduated from the Bartlett this summer. I'm a really bad public speaker, so I'm going to try and keep this like, as simple as possible and just strip it down to its various elements so I can go through the project. So I'm basically just going to talk about my diploma project, and the title of the project was Simulating a Crashed Architecture, and it's a project constructed from 4 crash simulations, but these crash simulations are architectural components, and they fit together to build a program of an architecture which is a roadside motel, which took its inspiration from reading the novel Crash. The project's not necessarily about Crash, it takes certain influences, but I'm going to just try and keep it. So I'll start off with the animation, and that'll show each of these components basically self-deform, and I'll show you. So there's an entranceway, a staircase, and 2 rooms. So this sort of imagines an initial impact, and the staircase is designed to sort of throw itself forward and deform. This is the double occupancy room. Staircase, the rungs collide into the balustrade. So I guess my sort of interest was it was about like the image, about image making, about how I could use technique of animation to get the images that I wanted. If I can just go this. Sorry, that was a. I'm really bad at speaking about work. I'm sorry about this, guys. I've totally lost my trail of thought now.
Can I ask you a question?
Yeah. That's probably a better way to say it.
Was it a kind of basic way of using the same parts in different operations, or was it totally different operations doing different things that you were later going to assemble together?
Yeah, I guess sort of. So we're given this site, and each component was like a test piece. So I started off with the entranceway, imagining this crash, and the architecture sort of, an extension of that, and how this entrance may sort of tear itself up and sort of violently rip itself apart. So that was the first piece. Then the second one was forget about these. So yeah, the entranceway, how it sort of, you know, it sort of deforms itself, and then the second piece was the double occupancy room. So it was I was looking at the novel Crash. I don't know if anyone knows about it, but it's about people have sex in car crashes. So this was like more intimate sort of space. It sort of brushes into the side of a house, you know, so it sort of deforms out of the house. So then these are the two. I'm really sorry, guys. I thought I'd be able to talk about my work more. I've not sort of visited this for ages, so it's a bit sort of taken me a bit by surprise. So yeah, I think I was interested in this sort of deformed space and about how that was sort of essentially more interesting than when it was constructed. So when it's constructed, it's all these sort of flat planes almost. It's almost when it's sort of like in a novel, when it becomes deformed, it becomes more sort of interesting. And this is the staircase. This is the multiple occupancy room.
I cannot stop to kind of draw connections between the work and Gilles' work, in the sense, not from a formal perspective, but from the fact that you are literally drawing people as these crash dummies, right? Like these kind of puppets, and it seems to be kind of overwhelmed by the nature of the event that you're kind of they're experiencing. And when I see Gilles' presentation, and it also, like, the human inside this architecture seems to be kind of just being so overwhelmed by this perhaps algorithm, or this house having so much intensity in its own definition of design, and so it seems natural to kind of draw some connections there. And was it like on purpose? I know that it goes with the aesthetics of the work, that it's really beautiful to work with these crush dummies, but it seems also that the human being is just an act of the physics of the architecture, rather than having a kind of a choice, perhaps.
Yeah. I guess the brief was it was called like the real and the unreal. So I think, you know, these were sort of standing for humans. They were and they weren't, and it was a lot of sort of play on sort of reality and fiction. So I guess nothing was sort of defined in a way, and that was the way it should be. I guess it was more about, like me just sort of enjoying the images and what could, you know, sort of the outcome of, you know, this sort of construction and sort of,
But at the same time, you are using, clearly, the composition is amazing, but by using also the physics of grasping, you feel the physics going around the context, because you are using the context, the real context in the finishing.
it's all like a backdrop.
And there I see ideas. It's inspiring, definitely.
Then this was me just sort of crushing
How did you define your experiments, and how did you move on to the next one based on the first one? Was there any things you were learning, or?
Yeah, I guess sort of I was new to animation, so each one was trying to make it a bit more sophisticated, and how it sort of, how the arms were sort of linked, and how it sort of tore itself apart, and how you could, I don't know, create this, not like because the spaces were random. I didn't know how they would look whilst I were making them, the joints, was only when I moved them that I realised it would make that sort of deformed space. So yeah, I was, you know, trying to add sort of levels of complexity so you get this sort of quite random sort of spaces as you would, as I would sort of progress through it.
Yeah, I see another parallel with Zero, which is it's all based on the articulation. You talked about a mass of springs in space, and in your case, although the pieces are more designed, it's all about the way they're connected, isn't it? Because in both yours and yours, you're designing those connections as much as the pieces themselves.
I also find it a very good example of a technique of collage, because you're in a way through physics collaging a car with a house, with a terraced house. And in a way you're also, I don't know if you actually, if the collision was actually using an actual collision detection or if you choreographed all the pieces. Because you could almost really compute it when you have this professional software, how you actually compute the physics of the crash.
Yeah, I went to a crash simulation centre. Realised that I wasn't advanced enough in sort of, you know, computing to use finite element modelling. But yeah, that would have been another interesting sort of step, definitely, in the project.
But I don't think that the simulation would actually validate more. It seems that, and we're going back to the conversation that we had with Jill a while ago, like this kind of pseudoscience approach, or to some extent, why does it really kind of validate the creative process when you're looking at a work like this, right? It seems that it's actually capturing, as Michael was mentioning, some of the physics of the crash, and as if that is kind of the driver, I see it kind of as, maybe in an object-oriented point of view, as an operational object in the project. And I don't know, like I'm not sure that the right way of doing it is just going scientific and just doing the right collision detection, you know, like it's always that kind of, you start wondering, maybe you just lose all the power of the work when you go there.
Yeah, maybe.
I guess it does have a lot of me in it. It's quite sort of, the project is quite introverted in a way. It's sort of my, you know, the way I sort of go about my work, I guess, is sort of,
You were talking about the fact that the RL is trying to be a bit less narrative, and we got the two extremes still. I mean, although you were trying to get a bit more narrative, it's still very functional, as in, I mean, Freyoto's experiments were very almost functionalist, and you have a very narrative-based work, which is hard to describe because the beauty is obvious and it's very powerful, but obviously it's harder to put words on it because you probably went through a very personal process of enjoying it
I sort of stumble over myself sometimes when I'm sorry I wasn't sort of...
No, but not all projects are able to present any projects. Some projects are sort of self-explanatory. But I think this parallel that you were saying, you're trying to get more narrative, in this case is quite interesting because you're still on a very functional sort of level. I'm not sure if you have any...
No, I mean, like I see, there's an obvious narrative in the project, right? But it's in a way, I mean, that was why I was going to that idea that in a way it's also a computed collage, because in a way there's also a certain, even though it might not actually be simulated but actually choreographed, but it's actually also trying to simulate a physical impact working through two different objects. So you could call that a narrative, or you could call, I would call that embedding meaning in matter, you know, like it's just kind of trying. I think that's definitely like, that's like, I find it interesting that there's this kind of layer, another layer of meaning acting within that.
I think like choreographing is probably a good word to describe it in a way. So it's got an element of like human control, I guess, to it. So,
Should we go back to this conversation maybe after the... do you have anything else to share with us?
No, that's it. I mean, unless you wanted to see the animation again, I have to see in a bit more.
Maybe we can just go to see like George work and then maybe go back to...
Yeah, that's fine.
Yeah? Thank you.
Sorry, I'm famously bad at presenting.
Maybe the work speaks for you.
6 years and it's never got any better.
I mean, brought the conversation.
Yeah.
The images are so nice. mean, it's interesting that
Yeah. I guess so you're working.
I mean, because it's very you know, it's like a really that's been it's been I think there's more
Oh yeah, definitely. Yeah, yeah. Yeah.
but actually see what
Yeah.
start.
Oh, thanks. No, just.
It's just this going on.
That looks like you work well together. Yeah, from there.
I'll just leave it like that. I mean, it's different. Sorry about the delay. Hey, I'm George Provenza. I've been studying at the AAC here at the Bartlett last year. Hello. Yeah, I'll just plug in Okay. Cool. So I'll just go through a few of the projects I've been working on recently. Originally, I did a bit of work like online, like making Flash websites for a while, and I decided that I don't want to do that for the rest of my life, so kept changing things here and then. And I've recently started getting more comfortable with programming, but also changing from just using code to display things on screen, like pretty graphics or animations, to use things like try to program things that are real objects in the real world. So there's quite a few things. I'll start with a more recent project that was done through Rory Glynn, which was works here at Bartlett and was one of my tutors. One of his projects, Fearful Symmetry, was exhibited at the Tanks this summer in August. And I had the pleasure to collaborate with him and do a little bit of code that mostly related to computer vision, as in making computers see and make sense of the world to a certain degree. And the other part dealt with kinematics, as in how, well, robotics and kinematics, how do you obtain natural movement from constraints within motors, servo motors. So I'll just start with a simple video of his work. And this was a somewhat sculptural piece, but dynamic at the same time. And the object of focus is this illuminated tetrahedron. And it was a massive project. It ran on a 12-meter long rail system, so you can move back and forth throughout the room. And the head itself was part of a simple type of a robot, a parallel robot called the Delta robot, called Delta because the base and the end effector are triangles. So in between there's two sets of joints with 3 legs, each connects. But in this particular piece, it was all about what feelings can be conveyed with very, very simple elements. In this case, like a clash between 2D and 3D, the flat triangle and the tetrahedron. And
to the presence and the absence of light. On my side, most of the things related to programming free Kinects that were attached to the robot and invisible to the viewer. They kept track of all the people, and we could see where they are in space, how tall they are, how many there are around the robot, which basically drove the robot. It gave it a few options for choosing behaviors. So whether there was more people at the same time, the robot would kind of like shy away and move away from the central point. Or if there was little, like none or few people around, they would try to find a random position where there's more people to interact with. And within a group that the robot would settle to, it would start moving its head towards and try to rather than focus on a group itself, focus on an individual. The second part of this project revolved more around natural movement, smooth movement. And for that one, we used the second robot, which was exhibited recently in Slovenia at Kibla. And this was part of the Robots and Avatars exhibition, the Slovenia branch of it. I'm sorry, but this isn't very right. With this one, the main challenge was getting servo motors which naturally move in a linear way. So you obtain the motion is kind of boring and mechanical, when as natural as humans we don't move that way at all. And the trick was, because the motors themselves were clever enough to have sensors so we could record its position, we started by looking at how people move and basically puppeteer the robot and store animations in a way and play with those to get more smooth movements. So this is going to be a really, really basic recording. This is like a depth scene recording of the robot in the workshop in B26. So this would be me controlling the end effect of the robot, and at this particular stage the robot is remembering all the positions. Afterwards, the robot can basically play back the exact same motion. So this is like one of the initial steps, a really, really basic one, simply record and play back. By doing the same motion, we would have this smoother movement because we would collect naturally interpolate each point. But the disadvantage in this is we would end up with a very, very dense set of points. So essentially a collection of 60 points of XYZ positions for each frame, which later on wouldn't be adaptable, we wouldn't be able to orient a certain motion towards a person, or we wouldn't be able to scale or dynamically adjust the timing to give it a different feel, which was the second part. So this is the only bit of code that will run tonight, which is really, really basic. Just using two joints of the head, the tetrahedron, and the stored position, and this is just showing a basic algorithm to extract the keyframes and simplify the motion. So on the left we've got two motors, motor 1 and motor 2, and we've got each individual position stored in time, but then just using a couple of simple signal processing techniques, I would extract keyframes, the points in white, and use them. So on the left, this is playing the exact same animation, 4 keyframes, and this is interpolating, so using a lot less data. And this would be just the velocity, it's just the acceleration on each motor. And if I zoom in, the timing, you'll notice it's slightly off. It's not perfect, but for a simple method like this, it does a decent job. Connecting again with basic stuff and moving to concepts more complex, for me a somewhat new idea was this of treating things as signals, systems and signals. So a system in a way it's kind of like a black box where you can input something to the system transforms it and outputs something else. And a signal itself, nerdy as it might sound, is actually a really, really basic concept. It's the idea of storing a property that changes over time at a constant interval. So for example, if we store the temperature in this room every 5 minutes, that would be our signal, the temperature signal. And that applies to so many different things like audio. Same thing, it's air pressure changing multiple times per second. And we look at the changes to analyze audio, and that's how audio filters are created. Same for images. It's just a 2D signal rather than 1D, and so on. So this is basically treating each motor's motions as 1D signals, smoothing out, like filtering, and then extracting the points of the peaks of the signal. And this will be kind of like the only nerdy part. The project isn't finished. There's like a second part of the project where at this point a lot can be obtained with just simple matrix operations and no inverse or forwards kinematics, which would be the correct way to deal with robots. The next step would be to integrate that and apply the same technique. But we'll see, hopefully, a new version of this soon. Other than this, which was related to my studies, I've been working for a company. I've been working for Daniel Hirschman, who is an artist who runs 2 companies. One is Hirschman, which deals with mostly commercial projects, and second is Technology Will Save Us, which mostly deals with teaching and trying to get people into computing, but more computing and electronics, like instead of paying again and again to purchase new products, reuse existing ones, learn how to hack electronics and how to get a better value and a better knowledge of the world around them, simply put. So now we'll go for the slightly more fun part of things. Actually, one bracket. This project at the same time, this was running at the Tate. I don't know if anyone noticed, there were some sounds playing on Millennium Bridge over the summer. That was a different project I was working on, but just one tiny part, which is the computer vision. What happened on the bridge was a 3D soundscape. So the volume, like the sound would travel on the bridge, but where the sound would end up was driven by a computer vision system. So we'd basically look at how many groups of people are on each side, on each part of the bridge, which was split into 3, and that would determine where the sound would go. So on that side, this is a snapshot of the OpenCV project I had running. So this is running, doing a background subtraction method, which for a computer vision technique is rather simple. It's basically comparing the current frame, in this case, with a history of frames. So there are about 100 frames, which you can see in the background section. It's a background that keeps learning. It adapts. And that's how, on the left, we can see the green outlines. We can isolate people. And also, if we want, we can run a cascade to detect individual people, which we can see tiny here, but it's not super reliable at this scale. simple CV, this wasn't the fun part from my point of view. It was more fun to see what happens over there throughout time. So we can see what happened in July. So 24 hours compressed in 2.5 minutes, 2.5 minutes. I think it's more interesting when it gets dark. The infrared sensor would automatically trigger at night. Somebody didn't know how to drive a boat. This was, I don't know, from my point of view, it was an interesting project to work on, but there were things which I wasn't entirely satisfied with. We knew what we wanted to get, as in a simple system where the amount of motion, the amount of people moving on particular sides of the bridge would trigger certain sounds, but because there were so many people on the bridge and the sounds would be controlled with so little difference, so little detail, I doubt that anyone actually realized that they were being tracked and that was what was controlling the sound, which is my only disappointment in a way with the project. But on the other side, it was a chance for me to tackle some interesting problems in computer vision. One of them was dealing with the change of scene really quickly, which is this problem. By default, the default algorithm cannot reliably be used to extract people because the lighting changes way too often. So a history of, for example, 100 images, which would result in the image on the right, isn't effective at this particular stage in time to extract this. This was solved later on, but again, moving from simple things to more complex things, it's interesting how whenever there is something that has to do with computing, if it stays on a computer, in most cases it will be fine. If it just lives on a screen, that's fine. But whenever there's anything that deals with the real world, there's a chance things might go wrong, and they will go wrong. So for me, it's interesting to learn more from these experiences. And I'll present 2 more short projects, which are more fun. One is actually was done a month ago in a store in Hackney, and in Dawson actually. And what we want to do is make the whole store play a sound, play a song. And we did that by creating loads of DIY instruments that would in turn create a mini orchestra to render the sounds. So that was quite a big project. I only did a tiny part of the project, which dealt with reading, understanding MIDI notes from a musical arrangement and converting that to a DMX signal, or basically converting that to voltage to control each individual instrument. And there are about 40 of them. So I hope there's sound on this one. Do you happen to know if we have sound on? We don't. Okay, I'll try to zoom. Speakers maybe.
When I think of Red Stripe, I think of, first and foremost, I get like a good feeling because I'm always curious like what they're going to smoke. I think of like they're sort of Jamaican, DIY heritage. So we're going into Dalston in London, and we're going to take over this corner store, and we're going to basically turn it into an orchestra where all the products on the shelves come to life. It's not just making a store come alive, it's actually inventing all the little ways that the store can come alive. So it's something that hasn't been done before on multiple levels. So that's always exciting.
For us at least, it's really important to be tangible, to make it something you can hold in your hands, see in space, understand it. So we just basically bought a lot of products in and played with them to see what we could get out of them. As soon as the experience is triggered, it's activated, it's like the whole story's coming alive.
This is the kind of project that's the most clever. We have Hershey Man, who are working with Stink Digital and KKL to kind of figure out how everything's going to function, how it's going to sound. The thinking behind the way we're filming this is that we want to try and capture it from as many angles as possible, being the least obtrusive to the experience. We're working with real people, so some of the challenges we have is just not knowing what's going to happen. We could literally have somebody walk up and take down one of our devices that looks like it's just a regular bottle on the shelf. If things aren't happening, we have to think, how are we going to change the experience on the fly? It's one of those projects that you don't know exactly what's going to happen, but I think we know that it's going to be a great experience.
This was probably the making of. Let's see if we can get the actual final result. Basically, each time a person would buy a red stripe in that shop, it would start triggering. So that was the final project. And the last thing I'm going to show tonight is a DIY project that's meant to inspire people to pick up programming and learn about electronics where otherwise they might not, and kind of call it trendy way. So this is a project running on.
Hi, Kickstarter. My name is Daniel.
My name is Kirsty. Hello.
We are part of Technology Will Save Us. Technology Will Save Us is a haberdashery for technology, and we call ourselves that because we believe everybody has a right to understand how to make things with technology. We do this with a series of DIY kits, products which help you to learn a very specific thing with each one. So for example, learning how to solder, how to program, how to build something with technology. So we're here to tell you about our latest kit called Bright Eyes. Whenever we create a new kit, we always pose ourselves a challenge. How can we inspire people to learn how to program? That was the challenge that we set ourselves when we created Bright Eyes. And we thought to ourselves, 74 LEDs on a pair of glasses that you learn how to program and control, attach sensors to do pretty much anything you can imagine. So the kit itself is made up of these pair of glasses, which are actually built out of PCB material, already pre-assembled with all the LEDs and the electronic components. You snap the bits together, it's so much easier than IKEA, so the actual construction is really, really easy for you. The most important part, though, is how easy it is to program, and there's 3 entry levels. The first one is super easy, and super easy involves copying something across to a USB stick. It's that simple. The next level involves actually writing a little bit of code, and that code allows you to add things like sensors, inputs, outputs, etc. And you do that by using a piece of open source software called Arduino, which has an amazing community already helping people to learn how to do things with technology and programming and electronics. And the third level, well, that's the hardcore level. You can do whatever your imagination and your abilities allow you to. You could potentially create something which involves sending your Twitter feed to your glasses, or you could have a CO2 levels registering and showing people how much CO2 is in the air around them. Or you could have the overall brightness of your LEDs dim based on the ambient light reading from a light-dependent resistor. The point is you can do so many different things with it. Kickstarter, we need your help. We've already invested in a small production run so we can work on all the kinks, the challenges, the surprises in production and assembly of something like this. We've now resolved all of those and we're ready to reach a much wider audience.
I'll pause it here because the Kickstarter project actually did finish and the guys actually did manage to raise the money for the project. So it's going live, and also you can find a few pairs of these in Selfridges if you want to check them out until Christmas. Sorry, that was way too commercial, but yeah. That's some of the stuff I've been working. That's me in a nutshell. Thanks.
George, how did you learn these things? So I see your Stack Overflow sticker.
Well, I started learning to code. The first step was really hard because I moved from graphic design, fine arts to computing. I ended up on this creative computing course at Goldsmiths, and I still remember the first experiences in a lesson about light and how that works. And I thought, like, well, playing with, I don't know, doodling and drawing, I should know something about how lights and colors work. But then the guy there started talking about electromagnetic radiation with a spectrum between 550 and 700 nanometers, and that was kind of, anyways, a bit too much for me. That was how the whole course was. So initially it was hard, but after that, just starting with really, really basic things, it started to gradually make sense. Initially there was like this massive barrier, but after that it actually gets enjoyable. So, yeah. Any other questions?
Where do you see yourself I can see a kind of path you might be taking in terms of making environments like attractive. Or do you have a sort of idea of how you might use that in the future? Are these your perfect projects, or what would your perfect project be?
I'm not sure about a perfect project. I've got like all these sort of like different ideas that I want to do for myself in a way, and I still haven't worked out how to do them like technically and how to manage them as well. But yeah, I would say I would keep doing things. I think physical computing is a really, really fun thing to do. Also challenging because real world challenges, like real world problems will always happen, will always be there. But the thing that I started learning while I was at the AC, and unfortunately I didn't have a chance to use as much, is to have a tighter connection between the physical side of computing and also understanding materials and manufacturing a little bit better, so there can be like a full circle between a simulation, something running in the real time, and the actual finished project in a way, a tighter feedback loop. And in the end, it kind of like boils down to having fun.
Should we move on and then we'll go back to
I think you still. Yep. Thanks.
Yeah. You guys hear me? Perfect. Okay. Is everyone tired already? No? Great. I'm trying to make it short. Let's see the resolution. It's okay. Cool. So my name is Vlad Tenu. I'm an architect. I've actually been an architect for like 6 years or so. So yeah, I just design buildings in my real life. But in parallel, yeah, I kind of do a bit of research. I kind of call it design research, but it's maybe it's more than that. So yeah, I'm gonna present you quickly the kind of research I've been looking at for the last few years. And I'm not going to talk about eggs. This is just a really good example that I thought I could start with. It is all about computational design, so it's kind of in the same agenda, but there's a very wide understanding of what computation can do and how we can use that to design. And there are quite a lot of people that are associating, obviously, computational design with nature, which makes so much sense, and there's so many things that tie up together. And all the correspondences between the computational process and nature are imminent, are there, and we know they exist. And what I try to look at, because there's this term minimal complexity that I'm going to try to define through just a couple of slides, which is the paradox between how nature organizes matter and a lot of things we looked at before, and why does the egg have the shape that it has, why it's not a sphere. We all know it kind of starts with a sphere, but obviously it is about organization of matter, and is about how gravity and how the actual world influences that. And I think if you guys are familiar, you've all heard Neri Oxman and Michael Hansmeier and other people talking about how form is generated, what is the nature of it. So what I kind of try to bring out of that was what is the nature of form, and what's actually the form of nature. What's really interesting is that as simple as the egg is, when we look at the shell on the microscope, we obviously see this. I'm sure you guys recognize the image. This is the structure of the eggshell itself. And it is interesting how such a simple form of an egg has actually got so much intricacy in it, and it is generated through so many fibers, very much in relation to what we've seen before, Giles project, Gilles actually. And it is amazing how in nature actually you find it at different scales. So whether it's in the same image here, we see the same kind of fiber structure. Well, actually we don't see it, but it's the eggshell. We see the nest itself, the egg that is created with the same principle, different scales, different materials, but it's got the same principles together. If we imagine we're in Beijing, we'll see this famous stadium we all know, and let's say it's based on a similar principle. And it all kind of goes back to when I got into computation at the Adaptive Architecture Computation a few years ago, 2008, and it all went back to this book that a lot of people kind of present. I didn't want to repeat it, but I think it's quite important to understand a bit of the correspondence between nature and computation and form as such. This is a very interesting image that I thought I'd quickly show, because it is all about process. Everything is process based, whether it's crashing, or whether it's looking at forces, or whether it's I don't know, heat exchange or whatever. It's a lot about process, and this is a very interesting one because it is a tree. We all see that, but it's actually not a tree that grew naturally. It's actually an artifact. Is nature, but it's actually an artifact. Is a mutant tree, if we want to say. It's one that a person, which is called Axel something, sorry I forgot his name, Gardner, but he actually took 8 trees and he started combining them, and through kind of gardening techniques, and created this amazing, I find it amazing kind of piece. It's more of an art piece, if you want to call it this way. And it is just showing that it's all about process and how we can affect process, how we can understand computation. It might help us understand what process means and how to apply it in architecture. And as we heard before, there's a big tendency of just taking a natural kind of system and scaling it up and transforming it to an architectural project that will be a Vorlon project or a vector field project, who knows. But what I looked at instead was actually minimal surfaces, and it all started with the dissertation project. And I think I'm going to skip through Friotto and most of you know them, and Gaudi, and kind of relevance of minimal surfaces in architecture. And I'm going to go kind of straight to a quick slide through the minimal surfaces self-organizing systems, which was the dissertation I had at the Bartlett at the Adaptive Architectural Notation. And it was all me trying to kind of cheat a bit, in a sense of minimal surfaces, all these mathematically generated surfaces, and obviously through particle spring systems. Jill described them before, used in simulation. You can make the create the association between solid fields and minimal surfaces, the corresponding between nature and computational virtual space. So what I've done, I reversed that order in not looking at them mathematically and looking through particle spring systems. What was interesting about this one was there was a scientific paper on this that I was lucky to present at Acadia in New York in 2010. What was interesting about this was looking at it in a different way. There's dynamic relaxation, there are a few other methods of creating minimal surfaces. This was purely looking at the natural behavior of solid fields and trying to generate them. As a kind of case study, I took the triply periodic minimal surfaces because you've seen before a couple of structures by Lou PH, which were quite inspiring for me at the time. So what I started with this project was thinking of fabricating and thinking of materializing these objects. It wasn't a pure imagery, it wasn't pure kind of 3D modeling. And there were all sorts of criteria embedded in these particle spring system in trying to generate the minimal surfaces. These are some animations of the code running. They're quite old actually. I would have improved them a bit in the meantime, but really had the time for that. And this is the way they were pretty much generated. What I would like to focus more on today is the fabrication side of it, and what's amazing about the triply periodic minimal surfaces, they all crystalline structure, they repeat infinitely. And what's interesting about them from the point of view of fabrication is a modularity aspect and a repetition. So for example, this one, the Schwartz B surface is actually generated by repeating a very small region, which is the 40th side of the cube. And as an algorithm, that's a different one, it's called Schwartz D. The dissertation was quite scientific in a sense of proving sort of theories and testing them, analyzing them. This is a different one. And yeah, the whole kind of idea of modularity and how to reach two prototypes. I'm going to skip this one. And yeah, it was quite an interesting process, and it was interesting. It worked in the end. It was a theory that worked. The code kind of started working really late in the day. There were many variations on how I looked at these surfaces, testing on quite a few of them. But I was still, as much as exciting was to see them all in 3D, I wanted to see them built as soon as possible. So what I got into was prototyping. Obviously, the first instinct of what the outcome of the dissertation was 3D print. I think I'm speaking a bit ahead of the slides. That's the prototyping bit. So that's literally the first piece I got out of the code, and kind of analyzed it a bit. It was quite interesting, the patterns it would have got, and what I started doing next was looking at the splitting it into the basic modules and trying to work a bit on the modules themselves. And I quickly looked at what would be kind of sufficient for keeping the curvature, keeping the aspect of the surfaces and trying to build them. and I've used paper. It's kind of a very simple approach. I try to detach a bit from my kind of tendency of designing and over-designing things, literally translating the research into physical shape. And started with these models. These were developed. I kind of continued dissertation. It was at a course called the Certificate of Advanced Architectural Research at the Bartlett. This was a test of the basic zones of the surfaces based on a similar initial kind of sculpture by Lou PH that kind of got me started on this project. There was a kind of really interesting connection with them, Sean Hown and the Lou PH guys. And then the prototypes kind of ended with what I thought is the simplest way of building them at the time. And just looking at the basic module, a kind of a 16 number of components for the whole piece. And what it meant was there were around 2,000 pieces, but what was interesting for me was that there were only 16 different triangles that were creating a huge amount of complexity. And that was the first piece that came out of that as a perspex piece. What was really interesting, the structural aspect of it as well, because as fragile as the small pieces were in the beginning, being perspex, cracking very easily. The whole structure was very stiff. It was really funny. It was actually in the Arabs Phase 2 gallery, and there was at the exhibition, there was a very funny kind of old engineer that was coming around the piece and shaking it and thinking and shaking it again. And it was all like going around it and shaking it again. It was really, really I had a bit of a chat with him, and he was still kind of trying to understand how, because the pieces themselves were really fragile. The day before, we broke a lot of the pieces, but in the end, the final product was very stiff. As the next stage, there was, I call the previous one the prototype, because kind of a prototype of what I had in mind. But actually, I was lucky enough to send a proposal for the text fabric competition that in which I kind of scaled it 2.5 times and reached a 4 meters tall piece. And I was lucky enough to win that. And as a result of that, TextFab have built it, commissioned and built it. With help from Eurohappel New York, and done some final element analysis on it, which confirmed again the structural capabilities of the geometry itself of the minimal surfaces. All the final analysis had really good results, no deflection or minimal at the level of millimeters. We've collaborated quite a lot on the internet and Skype. They've built a first kind of half-scale model, which was still 1.5 times or a bit more bigger than the previous one. This was from some polypropylene, very, very, very flexible material. Again, when put together, it became a bit wobbly from what I heard, but it became quite stable as well. So the final result was actually built in aluminium, and that was a bit of a challenging moment for the guys at TextFab as well, for me trying to think of the logistics of how to actually build it. Because all the segments, all the pieces became very big, it became quite difficult to manage, and the height again was a problem. But in the end, it was an amazing collaboration. It all got built. I was only kind of corresponding on site. For me, it was even more amazing to go there and see it built. It was pretty incredible as a kind of a spatiality gives in comparison to the photos. But it was kind of the beginning of a process of thought on how to progress with these structures as well. This is when it actually came to London. This summer has been the London Festival of Architecture. I have to mention in all of the cases, because there were so many pieces, I had so many friends helping me, so many people, that there's a huge list that I have to thank for in doing this. And it was incredible teamwork and a lot of friends helped me. But this last piece has actually around 2,400 pieces. And I'm going to finish with this one, which is the now the development of the previous one in a different type of minimal surface, and looking at minimizing actually the amount of components. Previously there were 16 components. This one is trying to look at just 2, and with a bit of a sacrifice of the continuity of the surface, I actually try to push that down to the limit of 2 components in kind of merging a few of those. And this is how it actually started, with a bag of polypropylene pieces, some kind of color coding. Again, this was realized with the support of surface architects and my colleagues there. And it happened in a couple of days. It was quite interesting to develop all the different shapes in order to kind of start building the whole, the fragments of it, which became fashion accessories quite easily. It was quite fun. There were some amazing days. And this got inaugurated as part of the Digital Shortage Festival. And I think I can thank you for that. If you still have some patience, I can show you a quick video of how that got made. That works. And it's been very simple. There was actually an idea of bringing this forward in terms of research, because there are only 2 components. They're very easy to put together. There's only such a basic principle behind it. And everyone that got in, actually, they just got it straight away. Yeah, it's a fast forward of 2 long kind of afternoons. And yeah, that's pretty much it. I think we could leave it here and this could run. Yeah, should I?
No, just like kick it out. Like, okay.
Okay.
Okay, thanks. So, I mean, we're going to go back now to the questions. We're going to open it for anybody to ask, but I'm probably going to start with one. And maybe I'm going to just go quickly back, because before I kind of forget, George, you mentioned something about the black box very briefly in your presentation. And in a way I felt that you were kind of sensing people, right? Like the Kinect, the computer vision, or techniques as well to just kind of sense people, and maybe this kind of links back to some of the other projects. And you mentioned that there was this idea of the black box as well, like that in the terms of the robot, sometimes you don't get access to some of the algorithms or APIs that maybe are in there, or in the Kinect as well. But isn't like as well, when you're kind of dealing with this data that it's so kind of unpredictable, don't you have a moment when you actually have to take a decision, right? Like you have to decide, well, maybe I'm going to do this or I'm going to do that, and it's not coming just from, let's say, the computation of the environment, but it's you basically that it's really kind of taking a decision and designing there. Maybe you could just comment on that.
Yeah, sure. Well, the idea of the boxes was even more general. It's just like the idea of a system in engineering. As you define inputs, outputs, and something that the box does. But then again, that easily relates to a lot of things around us. It seems kind of like natural. For me, the interest was to shift from like a basic way of thinking about things in code terms as simple variables or something, and seeing them as changing things, as systems that would evolve and change, and they're kind of unpredictable, which is what you mentioned. And the decision-wise part would be creating something that would learn by itself and change itself, but would give little control to the outside world. Or the secondary approach, which is the more basic one, as in we understand of the box and we deal with them individually and we simplify simplify complex systems, so therefore we can control it. That's how I look at systems at the moment.
You have to comment.
Want to join us? Anybody with
Actually, I saw the question first before me.
Sorry, I'm slightly bit of an outsider here. The last presentation was fascinating, but I'm not quite sure what the kind of end product is. Is it sort of feeling your way towards a building, is it a sculpture, or just experimenting with strengths? What's the end product?
Yeah. Should I take my story? Thanks.
In the meanwhile, you can think.
Yeah. Meanwhile, I can think of it as previously. Yeah, it is true. It is a research. That's why I didn't want to focus on final products. It is more about research about generating a geometry that's got an embedded intelligence, and the intelligence is not more than actually it being modular and being structurally very kind of functional, and it's got obviously applications in product design or industrial design or even fashion, if so. So it is a material kind of or design research. There are applications. I'm looking at the moment in obviously it's quite easy to design a lamp or something out of it. It's just a shape and you put a bulb in it. But I'm looking at how to use that kind of structural performance and the modularity of it in creating maybe furniture pieces, or in which it's a bit of an IKEA kind of, it's quite a cliche way of looking at it already, but you've got a set of components, set of flat components, only 2 or only 3 of them, and you actually can build your own chair out of it. So it is, there are quite a few levels at which it could go. There's also the architectural, that's how kind of all started, the architectural possibilities in this. And I think that goes a bit to double curvature and mirror surfaces in architecture. They could translate to panels, glass, beams, and so on. But at the moment, I didn't that's why I was kind of mentioning, but I didn't want to push myself into over-designing and trying to make the project out of it. It was just a series of experiments, and I'm kind of looking now at some applications for it.
Is any of this spinning off into your day job here?
A little bit. It's really hard. Depends on the practice, and in real life project, it's pretty hard to implement it unless I've had some discussion. Unless it's a playground or it's a, there was kind of an interesting conversations that I had with someone in terms of trying to build a similar sculpture with kids, and to understand to what level you can go, in which kids will actually figure out that there are 2 pieces and how they come together. And there's a bit of logistic that goes in that, but it will still be a play. It will still be a toy, let's say. What I would like to go is to kind of apply it in a product design way.
Because it feels that in a way, if it doesn't survive to the market, I mean, what is the intelligence of it resides in the structure right now, right? But from an evolutionary perspective, you would say, well, if it really doesn't become anything else, like in a way, it just gets evolved or like extinct, right?
Yeah, it is the same with kids as they get tired of a toy. They kind of play with it, they see what it can do, and after all, they throw it in the corner of the room. So it's pretty much the same thing, but it depends on the possibilities. I mean, it was quite interesting actually with this one that by mistake, some of the people I was working with, they connected the pieces in a different way, but actually started to create some weirdly interesting geometries that still made sense. It's a bit like creating Möbius curves out of the components that should have gone in a certain way. And it wouldn't have led to this geometry, but there was a kind of a possibility of error, which was quite interesting. I should collect some of the photos of the pieces that started to look quite interesting, change the rules a bit.
Well, I mean, just a continuation of it. I can talk now.
Yeah.
the idea of making it an architecture. I'm just, because you started saying, oh, this is not what I do in my real life. I do buildings, and actually just to come back to Gilles' project, because also in your case, I think maybe you took a more bold in terms of architectural statement where you actually said, well, it's a house. And in your case, from the question, I understand that people see it as more as an installation or an art piece. I'm curious for both of you, Gilles, like, have you ever tried to make it a full-scale thing, or has it always stayed in terms of the little model that you? I mean, it's quite big. It's the biggest STL model I've ever seen, but I'm wondering, because of the fact that STL is always flat, and have you tried to actually scale it up? And in your case, Vlad, have you thought of ways that this would actually literally, because you say once you were making, it was amazing in your presentation the way you made little pieces of paper, and slowly it became a bigger thing, and then Guru Hubble got involved, is even bigger, and then I was just imagining the continuation of the presentation where it's actually a house, and so I was curious if, just to continue this question as well on your side, if you see it being even more scaled up.
Yeah, I mean, it is. If I can take it quickly, it is a very very kind of actual problem, because it goes back to the images with the egg and the eggshell and the nest that keeps the egg. There are different scales and different ways of looking at it, and in a sense, scaling up the perspex piece into an aluminium piece, it kind of worked. Obviously, it was more complicated, but it reached a level that I almost kind of thought that actually the aluminium one should have been, because the material changed, because the weight and other factors change. It should have been maybe designed a bit differently, and components could have a different, I don't know, shape or solidity, whatever it is. So I think it goes back to the level of scale and how it becomes architecture or how it doesn't. I think it's a really tricky problem, and I think for Gilles as well, it might be the same challenge. And does it actually work the same, or maybe principles are the same, or it goes back to the question.
Right. Yeah, I think that this issue of scale, and especially the example of the eggshell, is really relevant. Because, for example, with our system, we've always said if we would scale it up, it would keep the same resolution. Like if we would do an entire building, it would also just be 0.7 millimeter thin fibers. But already on our model now, you actually perceive it as solid when you look from a larger distance, although it is completely porous. So it's an interesting issue, because you would probably see with a completely other level of scale work where you would scale this thing up while maintaining the same resolution. So there's a whole issue coming in. Like actually your whole design would completely change when you would scale it up probably. You would get a totally different spatial experience. Or you would have to switch to another material, and because like in my project we deliberately chose a very weak material, because then we need a lot of mass. So if you would do it in steel, it would be much more like a kind of like you wouldn't need so much material as we are using now. So there's a whole play between what material you use, what resolution, what thickness.
Well, in a way, it's also about material utilization, right? And you know, when you start your presentation, I thought, well, if I would know your work, right, and I start seeing your examples, and you talk about minimal surface, and I will talk about Candela, right? Like, you know, very first thing, and actually how to reach continuity with the smaller amount of material. And I thought your work was amazing because it reaches continuity through the minimum amount of material, but actually made of really discrete parts, but really tiny discrete parts. And I linked to Gilles' project, and you know, I think you guys should work together. And somehow, you know, you start building because you talk about 3D printing the house, right? And you know, that has a lot of implications. That's my question. Sorry, that's what I would like to discuss. But you know, have you thought about, you know, using discrete elements to actually talk more about emerging a material continuity through the very, very small components that can kind of emerge? You know what I mean? Instead of 3D printing the big chunk of the house and put together. You know, like when I see the metal pieces, I thought, you know, you can actually start building this stuff. What do you think?
But yeah, I think actually it's two completely different issues, because I mean, in a way, with I haven't showed this project, but I've done one other version with exactly the same working method as I was using, but using massive wood blocks instead of 3D printed particles. Because in my system, you could actually almost calculate it up to dust, like up to the smallest particle. So the smallest piece in that case is just a particle. But you could do exactly the same project using on a low resolution, using really standard building elements. But to go back to Vlad's project, I don't think the small element has anything to do with the overall scale of the element. Like, I'm pretty sure that the structural behavior is not coming from that small piece, but is coming from the minimal surface quality of the surface. So anything you relax, you can panelize in small surfaces, but it's not that the small surface is actually creating the overall form. So it's not an emergent piece. The piece it's a very top-down generation from an overall form. So that there's no feedback in between the piece, I guess, and the overall form. But what I would find interesting in case of your project, I'm wondering if it's possible to purely through the quality of relaxing, of doing this dynamic relaxation, if you could also do that on objects that are not mathematically predefined as what you are using. Like, could you imagine a relaxation of your own face or something, and would it have the same structural properties as your minimal surface? Or like could you go beyond that kind of predefined and rigid mathematical model?
Yeah, I mean, in this case, actually, it's not the way that the algorithm works is not a dynamic relaxation. It's all kind of a variable. It's got variable topology, so it doesn't kind of take a predefined mesh and relax it. So it's got like a top-down side of transforming everything into components. But the way it works in the beginning is actually there's a system in which particles are added and subtracted, and it's kind of, this is why it's got that kind of self-organization tag in the beginning, because it actually it assesses according to the level of resolution you want to give to the piece. Then it starts adding particles and removing, and it works out what the best solution is between them. The only mathematical constraint is following the basic principles of how trivial periodic minimal surfaces are generated. So most of them they're generated by this basic module, which is in a tetrahedron, and that all gets reflected several times and generates the main surface and so on. So,
but in principle, you could relax anything.
Yeah, in principle, you could relax anything. I kind of what this was focused on was mainly on the kind of mathematical series of surfaces, but looking at them from a more discrete kind of point of view in terms of using particle springs. But yeah, I mean, I think there's the conversation in what is top down and what's bottom up, and I think it's really interesting. And did you want to?
Yeah, can I just maybe to kind of turn a little bit the conversation, because I mean, of course this is really interesting, but it's like in a way your comfort zone, right? You take it there and everybody's just like, whoa, you guys. But I would put a different question, right? Like when you start scaling it up, that of course makes sense, but at the point when you really kind of maybe start scaling it down and you realize that perhaps the house that you're looking at, do you want to live in that house? Or maybe it's just a proof of concept that we can do it, right? And when does this kind of computational techniques maybe become a marketing tool? I mean, we know people in MIT or in different places in the world that are kind of driving a research that it has kind of a dual aspect to it, right? It's kind of actually selling the fact that it actually works. We are kind of minimizing material, building kind of densities and porosities at a micro scale. You cannot see them, but they're there somehow. But at the same time, they're kind of driving funding and so forth. How do you see your own work, maybe if it doesn't have an outcome, and if you accept at some point in a speculative future, right, that outcome doesn't exist, would you consider that still as this research as a kind of a marketing technique? Some people like in companies like, well, I won't say the name, but companies that are in Germany about robotics and stuff like that, they actually have a strand of robotics that is only about the marketing of the company, right? So is there a point where we're kind of maybe fooling ourselves that this actually is kind of the perfect kind of complexity being minimized to that kind of optimum form, or we're just kind of driving a narrative that is actually kind of supporting our potential new future as architects?
I mean, like in my case, it's definitely the 3D printed house. We call it a kind of self-fulfilling prophecy, because it initially started, we totally didn't believe in it. It was just a DRL project. And then you actually go talking to the people that are in the business, and they really find this a very normal and absolutely not alien wish to 3D print a house. They're really just sitting there and saying, okay, this makes sense. They invest quite a bit of budget in really researching this, and we've since the 3D print show, we've been talking to so many people in the industry, and right now I actually believe it's not science fiction. Like this will really happen within 5 to 10 years. Like it's really not. So it becomes a kind of self-fulfilling prophecy. So I don't know that in your case.
Yeah, I mean, I could just pick up quickly on the word optimization, which I think a lot of people use, and especially in relation to nature and even topological optimization itself. You can call this a natural process itself, and a lot of the others. But actually, optimization is a word that's in relation to nature. It's quite a paradox, because nature, even if it optimizes how matter works, it actually doesn't, because it actually creates such complex structures that until very recently were unimaginable in like 3D modeled form. Now it's kind of possible to visualize and manage huge amounts of data. But the way nature works with it is so kind of luxuriously exuberant, and it's got millions of cells and particles. And if we're talking here about marketing and architecture and materializing they can very easily, the fine line between them can very easily split into two totally different kind of categories or eras. So that's where I think the word optimization actually is looking a bit back at. And obviously 3D print is evolving so much now that I'm sure in the future we will 3D print buildings as kind of a lot of people are anticipating. What is interesting is actually understand how the market, how the evolution of the market is, and how possibilities and budget. Because if the 3D printer's house is gonna cost, I don't know, the whole budget of the whole world and Mars kind of combined, then the whole kind of research will instantly focus on, okay, how do we reduce that budget to the minimum possible? What if there's a process in which you throw paper at it and it kind of starts, I don't know, I'm just kind of throwing words out, but yeah, I just thought I'd pick up on the optimization side of it.
I was just wondering, the podcast, what came first, the algorithm, and then did the housing typology come after that, or were you thinking of housing and then this algorithm came after that?
I mean, we developed like the basic algorithm that is underlying our own algorithm, is what Vlad was mentioning, the topology optimization. So topology optimization is an algorithm that takes out matter out of a solid block of material, and it takes out all the matter that you don't need to achieve a certain structural condition, to reach a certain stability. And it's a very spatial thing, because your structure and your space kind of coincide. So we initially in DRL developed a massive catalog of 200, 300, 400 possible setups how to generate space. So we were really cataloging the spatial opportunity within the algorithm. And after a while we knew exactly, if we set up a system in this way, we will get this kind of space. And in the end, to design, we were following a more iterative process. So we would start out with a solid block of matter. We will generate a first spatial condition, and then we would just literally take it out of the algorithm, start manually modeling and tweaking it to how we want it, because in the end we're architects. I'm not interested in the perfect structure, I'm interested in kind of something that is influenced by matter but it still has spatial quality. And then you would, the thing you adapted, you would throw it back in the algorithm, you would give it one more session, and you would keep going back and forth. Because in the end, as the algorithm, like topology optimization, doesn't know that humans need flat surfaces to walk on. So you need to force that. You need, in the end, we even had stairs in there, and the stairs obviously come purely from deliberate design intent, from like just as an architect would do. Like I want my stairs here, and there they go. So.
Just on Jose's point, but to Tom and George, because in a way, thinking of, okay, where do we take this to the real world? I was just wondering, Tom, your ambition was images, or like I'd like to know, because for example in George, I know that the thing is the thing itself. So it's sort of simple. But I'd like to know for you, what did you have in mind in terms of your objectives, and how did you take it from there?
I don't know, I guess I was just really wrapped up and interested in the project within itself, that I had no sort of overriding
so was it
view of
the process?
Yeah, it was just of the process. Yeah.
But I think it was interesting that like the last Nexus we actually had people from Factory 15 here, and I think that we're going to be that default mode where we actually think, oh, we have to go to the material world and we just need to build that, and there's very little room to build, right? You actually have lots of architects without jobs. We have very little work out there, and it seems that right now just putting it out there is not the most relevant thing, right? Some people like Factory 15 and the work of George could suggest that maybe the work at that level has some potential as well. I mean, lots of potential. I mean, we saw some work that is it's driving huge budgets, and we somehow, in our architectural direction, seem to kind of just navigate one only output. I feel like I'm very happy to start seeing that, you know, different architects, in something maybe that we spoke with Jill in some points, like what are these kind of possible outcomes that we can deal with the way we're thinking, designers. That's in a way the Nexus is trying to kind of put a big kind of bring people together about computational design or design in general as kind of a creative form of production, right? So I don't feel like we need to kind of reach that convergent, let's say, built work that okay, that's real, right? And if anything, I mean, I would start thinking that most of these kind of, I wouldn't say just virtual, but outcomes that could influence the built environment or anything really have their own value. And if we don't evaluate them like that, we are just undermining them. We're just kind of saying, well, this work is not built yet. It's actually getting there. And the ones that hold the power to actually build are very few. So I'm happy to see and celebrate some of the work that it's definitely not built and might never be built. Right?
Otherwise you wouldn't do anything, would you, I guess? You'd be too scared to do anything if you question stuff too much, I guess.
It's a level of creativity that is based on that, and a lot of the most pragmatic outcomes can come of a pure abstract process. And I've been through it at certain moments, and I think a lot of us did, and it's quite, I think there's a very fine line between crazy ideas and real life. And I think a lot of us, we're actually talking about real things, you know, even topology optimization using car industry and so on. And it's got so much potential, and us being, as architects, being able to get a bit in control of that, I think it's really powerful. And, you know, we'll worry, let's say, about the evolution of 3D printing a bit later, but I'm sure when that happens, then everything will come together in a, you know, quite a solid way.
I was fascinated that the houses that Jules' algorithms built looked a bit like cave dwellings, this kind of reversion to a natural state. Is that a coincidence, or is it telling us something?
I mean, that's pure coincidence, of course. It's actually funny because some people on the internet also, part of Linus service, it was also compared to cave dwellings.
just want to go a little bit to the previous point you made, but just a minor addition. I myself don't come from an architectural background, but I ended up at the AAC last year, which was like loads of fun. From my point of view, one major step would be going from using tools to making your own tools as an architect, which would open up this whole new world of basically not relying on the limitations of software companies giving features to you, but making a connection between your ideas and how you can realize them by yourself, you know. So that's one major thing. And the other is, it can be, I don't know, for example, on the course, you were taught a language called processing, free, open source, really fun to use. But from my point of view, the more important thing is actually understanding logic. And once you understand how to use one language for example, you can use any other, and that again branches. It's kind of going one step further. So rather like from moving to using CAD packages to making your own tiny tools, then from realizing that actually from making tiny tools you can actually code pretty much whatever you want, depending on how much time you have available and how much willingness you have to go into details. That just opens up so many variants, whereas you can start working on some architectural projects, but then explore any other thing for fun, where computation can be used. There's so many different areas to explore.
Well, I guess we're gonna leave it there. We will hope that you guys stay a little bit, just maybe if you want to speak to some of the people that presented today. Enjoy the bar as well. And I hope that to see everybody in a month. You're willing to come again. And thank you for everybody that presented and America as well for joining us today.